So let me start off talking about anecdotes from hundreds of UVM adopters. So when Tom was preparing this tutorial and set the title as Tales from the Trenches, I thought, yeah, we've got a few things to say in terms of Tales from the Trenches. It gets pretty dirty and sweaty out there in UVM land where folks are starting to adopt this stuff. So what I want to do is to present the adoption of UVM from the point of view of ordinary folk who are trying to use UVM. So this isn't particularly a presentation aimed at experts. If you're an expert, you're welcome. But generally speaking, we find that experts can look after themselves pretty well. Experts in any subject area look after themselves pretty well. So what I'm going to try to do here is to give more some feedback from what most ordinary users would say and do say to us at Doulos. So as you know, we run training classes and we've met and talked with a lot of ordinary users trying to adopt UVM on regular projects. So I'll start off with some very general comments on the adoption of UVM. Then I'll go on to talk more specifically about migrating from OVM to UVM, and then get really nitty-gritty and talk about some of the specific pitfalls. So very general comments. What do you need to know if you're really seriously considering migrating to UVM? Well, first thing, don't underestimate the learning curve. So there's two groups of people who are particularly prone to do this. One is engineering managers, and the other are people who are trying to teach themselves UVM and System Verilog. Oh, I wish I had $1 for every time I picked up the phone to an engineering manager who says, I've got a team. My team want to learn System Verilog and UVM. I've got a budget that's this big and they can have 3 days off their project to go and learn System Verilog and UVM. If that's you, you need a reality check. It takes a lot longer than 3 days to actually climb this learning curve because there's a lot to learn. Next issue that comes up again and again and again is folks who start adopting UVM, they go on a training class, they start building up these magnificent verification environments, but they're still doing directed testing and still working out how to tweak a particular feature in the design under test by writing a particular test. Folks who do that won't really get benefit from using UVM. You have to move to a constrained random approach. Third issue that comes up again and again and again when trying to teach people how to use UVM is understanding that it's all about reuse. UVM exists for the purposes of code reuse. If you just want to write tests, there are many, many easier ways of writing tests rather than trying to get immersed in this whole area of constrained random verification and object-oriented programming. The benefits come from code reuse and know-how reuse, and that requires a lot of expertise. So another theme that comes up again and again and again is the need to become good software engineers, the need to learn object-oriented programming techniques, and a lot of techniques that are borrowed from the field of software engineering. Another very distinct general point is understanding that UVM or any specific methodology will only get you so far. UVM gives you a platform to build on, but by the time you've learnt all there is to learn about UVM and become a UVM expert, you've just got a better platform to stand on. But you've still got a lot of work to do that's going to be very specific to your particular application. So a lot of the work you need to do in creating real verification environments is going to be specific to you and your company's problems. Okay, let's talk about OVM to UVM very, very briefly. I'm not going to go into a detailed laundry list of what you need to do to convert from OVM to UVM. I know a lot of the later presentations today will give you people's very specific experiences on what happened when they went through that process. I'll just to say, having done it myself on a number of occasions, it's a fairly straightforward process to take an existing OVM code base and convert it to UVM. There are plenty of guidelines on how to do it. So Cadence wrote some documentation on going through that process. Mentor created some documentation. We at Doulos have created some documentation. So There are places you can go on the web to find the ABC of how to convert OVM to UVM, and later speakers today will give you their specific feedback on that process. So more general issues on UVM now in particular. If you're here because you want to learn about UVM and learn about some of the pitfalls to look out for, first thing to be aware of is that UVM isn't all straightforward. Some of it is pretty clean. As standards go, it's been cleaned up a lot. It's quite elegantly defined, but many of the UVM concepts are not straightforward, and the documentation is certainly not enough. So it's not sufficient just to go read the UVM reference guide, read UVM user guide, watch a couple of videos and dive into it. Many of the UVM concepts require some elaboration. They require a good understanding of how to apply them, and that you're not going to get just by Googling UVM on the web and looking at initial documentation. Many people say that the terminology in System Verilog and UVM is a barrier to adoption. The sheer size of the UVM base class library can be a barrier. We've delivered a 3-day UVM training class for a number of years now. We're about to move it up to a 4-day UVM training class. We find even when we take folks who know OVM or know VMM and are trying to learn UVM, it still takes a good solid 3 days because there's a lot of detail to assimilate in terms of getting into the UVM library. There's lots of detail. People also very often complain that there's too much choice. UVM does give you choice, it does give you options. There's a good reason for some of those choices, and that is backward compatibility with legacy methodologies. So UVM has retained backward compatibility, in spirit at least, with its ancestor methodologies, and that means there is code kicking around in UVM that's been there for many years. In some cases, I'm sure people have forgotten what it was written for and quite what it was supposed to do, but it's there anyway in the source code. Common comment that people come up with: whose UVM are you going to write? Are you going to write Cadence's UVM, or are you going to write Mentor's UVM? And then on top of that, although UVM is a methodology, it's not a complete methodology, and people comment that there's a lack of recommended practice and a lack of naming conventions within UVM. You could argue that you need another layer on top of UVM, yet again, to say how to use it, which I'm sure a number of providers are working on. Okay, so those were all general issues. Now let's get down to the nitty-gritty. And what I'm going to do is to identify what I think are the top UVM time wasters. And the criteria here is the amount of noise and aggro that I've heard from our users as they start to learn and use and apply UVM. These are the things that come back to me most frequently from real users in terms of what's wasted our time. So here's some great big pitfalls for you to carefully step around and avoid falling into. So top time wasters I'm going to talk about: field macros, do macros, deprecated mechanisms, confusion over the configuration database. I'll just pick out a few of these things. So let's start out with those evil field macros. We know they're evil now because last year at this very conference, Adam Ericsson won Best Paper Award for a paper telling us how evil the field macros are, so they must be evil. Now, these are the field macros in UVM, which came from OVM, which came from some of the legacy methodologies. Are they a good thing? Are they a bad thing? You make your own mind up. I'm not going to revisit all the theoretical arguments whether you should or shouldn't be using these macros. I'm really going to focus on what customers tell me seemingly every day of the week. Oh, I wish I had $1 or even a cent for every time some customer had told me about the time they have wasted trying to understand and debug these field macros. So put aside all the issues of whether they're a good thing or a bad thing, or that you should be using them or you shouldn't be using them. The fact is that this isn't the top of my list for user aggravation. People start using these things because they saw them on a tutorial. They Googled UVM and started going through somebody's tutorial, and it used UVM-to, so they started using UVM-to, not having a clue what do does, and then wondered why they were wasting days, weeks of their life trying to debug this stuff. So these are the field macros. The field macros generate loads of code, and in principle, that's a good thing because it saves you the trouble of writing all of that code yourself, and I wouldn't particularly have an argument with that. Except it soon gets a lot more complicated. So these field macros have flags associated with them, and you set individual flags on individual fields in your transaction classes and your components, and those flags then control the functionality of the code that's generated by the macros. So far, so good. There's a great big list of flags. If you start going through the UVM documentation and hunting down what these flags actually do, you start to smell a rat. Because some of the documentation is suspiciously terse. And you think, has this been reviewed since it was written? So you go and hunt around in the source code itself and find the source code is full of all sorts of interesting code that doesn't appear in the documentation. And you start getting really worried. Well, basically everything starts off being switched on, and you can knock out functionality field by field, operation by operation, by setting these no flags, no copy, no compare, no print, in order to exclude a specific field from a specific operation. All sounds very sensible. However, it soon runs out of steam. So if you want to customize the behavior of the methods in your transaction objects in a more algorithmic way. So, for example, you're trying to do a comparison between a set of fields, and the comparison between one field depends on the value of another field, or the same for any of the other operations that are generated. These flags will run out of steam, and sooner or later you'll have to start overriding methods, which is reasonably straightforward to do, except it immediately causes endless confusion, particularly amongst the self-teach guys. Notice, Cliff, this is an advert for training classes. Do come on training classes. Don't teach yourself this. Well, I would say that, wouldn't I, because I sell training classes. But it's also true. So if you want to compare two transactions, you call tx1.tx2 to compare two transactions. If you want to describe the behavior of transaction objects when they're compared, you don't override compare, you override do compare. Do compare is a user-defined hook within the transaction class. And do compare has a comparison policy. Start looking up comparison policies in the documentation, and, well, then come back to me and tell you what you find. So do compare you override. Compare as a couple of objects. You then call compare field of the comparer object, and this is doing some work behind the scenes. But as a consequence, you can create your own user-defined behavior for comparisons. You can also write field macros. What happens if you do both of these things? Well, you can do both of them, and you'll get both lots of functionality. So what we're doing in this particular case is switching off the default functionality that's being generated by the field macros. We're just using the user-defined functionality here. And turns out one of the things that the compare field function does is to collect a set of mismatches, and it builds up an audit text string that gets printed out at the end when we finished our comparison. All well and good. Only what happens if we start trying to do both, which you can? Well, here's what happens. So suppose we compare two transactions. This is a bit of pseudocode for what the implementation of compare actually does. So the implementation of compare, first of all, shoots off and executes all of the code that was generated by those field macros. So it does all the automatic stuff, taking into account the flags that you set, compare or no compare. Then it calls your doCompare method that you may choose to override. So we're actually overlaying these two sets of behaviors, the built-in behavior and the user-defined behavior. Then it prints out the mismatch report. So here in doCompare field, we're building up a mismatch report, then gets printed out at the end by this output mismatch report call. If you run this, you'll find you don't get out all the mismatches, you just get out the first one. It prints out the first mismatch. So if you want to customize that behavior, you can start looking at the comparison policies. So let's see what happens if we get into comparison policy. This is a jolly complicated way of doing things. Anyway, what we can do is to create a comparison policy object, set its attributes, and pass that into compare. So if we create a comparison policy object, set the maximum number of mismatches up from 1 to 999, now mismatch report will print us out a great big long list of mismatches, which is all well and good. That works. So we hunt round in the documentation of UVM and find that our comparison policy also allows us to define comparison types, whether we're doing deep compares or shallow compares. So if we set our comparison policy to shallow, to say we want to do a shallow compare and do the same comparison, well, cut a long story short, it doesn't do exactly what it says in the documentation. In fact, it doesn't do much like it says in the documentation at all. In fact, it doesn't work. And talking this through with people, it seems that there was some vestigial code left over in the UVM base class library. There's quite a few fragments of code left over from supporting legacy methodologies, which hasn't quite been brought up to date and carried forward in the current implementation. And this is all part of the joy of adopting UVM and the challenge of doing so. You have to know what you're doing. There's plenty of pitfalls around there to avoid. If you're an expert and you want to use all of this stuff, it all works, and I've got no issue with it particularly. If you understand what you're doing, it works. My advice for new adopters is stop faffing around. I don't know, is that just a British thing? I don't know. Stop messing about. We haven't got time for all this messing about. So what I would recommend you to do if you're just getting started is just override do compare and just regard it as a simple function, compare two transactions and return yes or no, it matches or it doesn't match. And then you can actually grab back a lot of your life from all the time that you would have spent trawling through the UVM documentation and starting to debug things. Another issue, the dreaded super.build build phase. Oh, I wish I had $1 for every time I've talked to a customer and started explaining UVM and they said, oh yeah, we got caught out by that. We wasted 3 weeks trying to debug our design because somebody had been messing around with this stuff. What happens is, if you register a field for field automation with a field macro, then in the build phase method, one of the standard phase methods, in this call to super.build phase, the build phase method of UVM component actually has a call to apply config settings. This is a one-time thing that happens once during the build phase. Apply config settings will then match the names of any registered fields with values set in the configuration database. And if the field name matches the field and the path matches and the read-only flag hasn't been set for that particular field, then the value of that field gets set once to the value of the configuration database, which is a perfectly good mechanism. It works, it's well defined, but you have to know about it. And my only complaint about it, or at least the complaint that I've heard from so many users, is apparently not everybody knows about it. And if you don't know about it, then it can get really confusing what's happening in this situation. So people typically find that the values of their fields are being mysteriously initialized, values that they weren't quite sure where they came from. Or the other side of the coin, they set all of this stuff up so that their values were being initialized and suddenly they stopped being initialized because somebody decided to delete this super.build phase call. So don't get caught out if you're a newbie with this stuff. Then some moderately evil macros, the moderately evil UVM do macros. Oh, I wish I had $1 for every time somebody had told me some horror story of the time they spent wasted trying to debug these things. On the face of it, it's all very sensible. So you can write a few procedure calls to create transaction objects, handshake between sequencer and driver, randomized transaction objects, or you can wrap up these procedure calls in a single one-line macro. That seems very, very sensible thing to do. I don't particularly have a problem with that. I don't have a problem with that in theory. My only issue, and the only reason I'm telling you about it, is the number of times people have told me they just wasted hours of their life debugging it. Let's see what UVM-do actually does. Well, I went through the exercise of expanding it the other day, so in the latest version of the source code, this is what it expands into, which is not too horrific. So we are, UVM object wrapper. Well, I wouldn't write that in my own code. Anyway, get type, not too bad. Create item, well, it creates an item, blah, blah, blah. If you look at what this code does, it's all fairly sensible. It's all reasonable code, but it's not really what you want springing up in the debugger or having to deal with. So a couple of weeks ago, I was running a training course. I presented this theoretical picture to the guys in the classroom and said, there you go, I've told you, this is what's going to happen. What happened? Very next lab, somebody wasted an hour because they wrote UVM-do, and there was a compilation error, or rather a runtime error when they started their simulation, and they just scratched their head and stared at it and couldn't work out where this error was coming from. Because if you just got some runtime crash and you're new to this game, how do you know where it comes from? And because if you're new to the game, you're not quite sure whether you've done something wrong, and if you've done something wrong, where do you start looking for what you've done wrong? So they replaced this code with this code, saw where the error really was, and then actually saved a bit of time trying to debug it. So again, nothing wrong with this macro in principle, and if you're an expert, go do your own thing. All I would say is, I have heard an awful lot of people wasting an awful lot of time trying to debug these things. The sequencer library from OVM. So many times I've spoken to people, typically people who've learned OVM themselves or are trying to move from OVM to UVM without a safety net, trying to work out how to do sequences in UVM and getting totally hung up about the way they learnt to do sequences in OVM. OVM had a way of doing sequences that was truly evil in terms of the amount of time that it could waste for people. So OVM had macros like OVM sequencer utils, and OVM sequencer utils populates your sequencer with an initial bunch of sequences, including simple and random and exhaustive sequence, and the random sequence runs by default, and the random sequence picks another sequence to run, but not the random sequence or the exhaustive sequence, which only leaves the simple sequence. So it runs that one, and it does it a random number of times, and you start adding your own sequences to the sequencer, and they get picked at random as well. So as a newbie, you create your sequencer, it's just a sequencer, and it starts doing weird stuff. And then you start adding your own sequences, and it runs those sequences sometimes, but then it mixes in other sequences as well, and it all gets deeply confusing. It's all gone now. Also, OVM sequence utils has gone. OVM used to allow you to override the default sequence and override the count of the number of items that got generated at random by using these setconfig string calls. This stuff has all been deprecated in UVM. There's a different way of thinking about running sequences in UVM. In UVM, conceptually, it's very, very simple. If you want to run a sequence in UVM, you start the sequence on a sequencer. You say sequence.start sequencer. That's fundamentally the way of running a sequence on a sequencer in UVM. So here, sequence is the sequence we're running. We're running it on our sequencer. Parent sequence is the calling sequence, the sequence that's calling start. Priority is the priority of the sequence. It's as simple as that, conceptually. And of course, people then think, well, how can I go back to creating a sequence library? I've always thought about sequence libraries. I want a sequence library. Well, UVM has a sequence library. At least it has a sequence library in draft form that's part of the release. It's the UVM sequence library. Don't confuse this with the OVM sequence library. The UVM sequence library is okay. The UVM sequence library is fundamentally just a sequence. It's a very, very smart sequence. So here, when we're extending the UVM sequence library, we're really just writing a fancy sequence. You can then add your sequences to the library, and finally you start that running by calling it start method. So the thing about the UVM sequence library and the pitfall here is don't regard this as the standard default way that you should be starting all of your sequences. In UVM, there's a very, very conceptually simple way of starting sequences. You call start, and that starts sequences. And the UVM sequence library is something that you might want to look at if you want to build a library of sequences and then have them selected according to some technique. Okay, so coming to the end here, other detailed UVM issues that people whinge to me about a lot. One is the need for runtime phasing. Runtime phasing is an ongoing debate in the UVM community. There is some runtime phasing in the current implementation, but there are also health warnings because the Accellera Standardization Group are working on improving and polishing up the API for runtime phasing. Well, real users need runtime phasing one way or another, so let's hope that gets sorted. There's also a lot of confusion over when to raise and drop objections. I don't think there's a fundamental intrinsic problem here. I'm just relaying it as this is what ordinary folk tell me. People seem to have a lot of confusion about when to raise and drop objections. Also, people seem to find the register layer hard. A lot of folks have said to me that they started trying to get into the register layer and they just got overwhelmed by all of the detail here. And again, I don't think this is an intrinsic issue or negative point about the UVM register layer in particular. It's pretty cleanly defined, but there is a lot of it, and therefore the learning curve is quite steep to get into it. Other issues that people raise a lot: how to handle layered sequencers and layered agents, how to deal with multiple protocol stacks, how to handle interrupt sequences, confusion over what lock and grab are supposed to do. And at this point, I want to advertise the hardcore UVM session that we're running later on this week. So during hardcore UVM, I'll be presenting a paper where I'm going to go into lots and lots of technical detail on UVM sequences, virtual sequences, locks and grabs, and all of those things. Also, Janik and the other guys from Synopsys are presenting a paper I'm looking forward to called Creating Truly Reusable Protocol Layering. So between us, we're going to cover a lot of the ground here, where more sophisticated users run into a brick wall with UVM thinking, okay, I've learnt the classes, it's only got me so far, how do I take the next steps? Okay, so I'm running to the end of my part of this tutorial. Just to finish, things that are missing from UVM. So again, this is a digest of a lot of comments from many, many people. One thing that people whinge about a lot is mixed language support at the register transfer level. And there they're really referring to how to use a UVM verification environment on top of a mixed language design with a combination of VHDL and Verilab code. Well, I know it works. It works with all of the tools. The issue is, I guess, it works with all of the tools in slightly different ways. So exactly how you successfully build a mixed language design where you're instantiating Verilog within VHDL, within Verilog, within VHDL, there can be some tool-specific differences. Mixed language support at the transaction level, another topic we talked about a lot at DVCon in recent years. And each of the vendors has excellent solutions for transaction-level mixed language support, because the issue today is that they're not totally standardized, so we've got 3 slightly different solutions. And then the third thing that some users complain about a lot is using UVM with analog and mixed signal designs. I know there are some papers in, I think it's one of the tutorials this afternoon on analog and mixed signal that raise some of those issues.
So I'm going to take a little bit of a different approach regarding to the first presentation in terms of going and talking about all the issues that you deal with migration. The main point of this presentation is to kind of figure out how to hide all this stuff from users and to enable users to move from OVM to UVM without seeing any of the pain or realizing that they're actually now moving to UVM. So the whole goal for us is, at least for that presentation, is to make the migration look like just a simple OVM version change. So in this presentation or tutorial, I'm just going to present a OVM compatibility layer that was implemented off top of UVM that will allow the use of OVM-based IPs on UVM source code. So we have tons of OVM IPs today, and just trying to migrate it and move that is just not a simple process. You go into a lot of issues. We've done that. We went through a lot of that in the past, and we're not willing to take that chance and affect, at least at the time being, our resource and as well as time schedule. So we wanted a different approach to figure out how we move to UVM in a more easy way. So we're also going to look at the results of using this compatibility layer by migrating an existing SoC, which was consisting of about 25 plus OVM VIPs. So as I said, we're going to kind of demonstrating a case study of migrating the SoC environment fully from OVM to UVM, but actually without converting any of the OVM code. So we're not going to touch any of the OVM code. So as everybody knows, and I think the first speaker also hinted through that, so UVM recommend that you run a converter script on the source code to kind of replace your OVM start symbols with UVM start symbols. So there's a script available today. You can just run it and convert most of the O to U for you. But that's not enough. You still have to do a lot of code. So especially if you're borrowing a lot of legacy code, it depends on your use model. I guarantee you're going to run into tons of issues that you have to deal with. And the biggest problem you have to deal with is how you're going to get your simulation passes the same way it was passed before. And that will take a lot of effort, a lot of time. And definitely, I don't want to be the guy debugging this. So this mandate, either you abandon the OVM code of the VIP, or you'll have to maintain two repos, one for OVM and one for UVM. And with our heavy use of OVM, this is not practical, at least for us, because as VIPs need to go into the SoC with OVM and UVM base running in parallel. So this was not a solution for us. At least for our SoC, we cannot adopt this. If I try to go to our internal VIP guys, and I'll tell them, oh, let's try to convert, I know I'm not going to get the buy-in from them. As I said, we've done this, and we run into a lot of issues, and I'm sure their management will say, we're not going to do that. This is too much resource consuming. This is too much. It's going to have a lot of impact on our schedule. We're definitely not going to do that. And if I get the VIPs to agree, the VIP managers, and I go to our SoC folks, they're going to say, yeah, we'll move. We'll give you the SoC. Go ahead, convert it, prove that it runs all the regression, have all the test beds the same way they were passing on OVM. Maybe we'll move. So we wanted a different approach, and definitely I didn't want it to be the guy taking all that code or the people working with us and trying to migrate those projects. So we started looking at a different approach. How can we take our existing OVM code running on UVM, but without putting the burden on the project or without affecting our execution schedule as well as our resources? So we realized that we really need a compatibility layer. So we peeked around, we started looking, we talked with all the UVM folks, and then we found that Mark Glosser at that time he was working for Mentor, so at that time he had a compatibility layer. He started one, I think he didn't complete all the way, so he kind of pointed us to what he had at that point. So we took that, we enhanced the compatibility layer, and we made it work with UVM 1.1 release. So this layer sits on top of UVM, and what it allows you to do, it allows the migration to UVM without having to modify any of your OVM code. So if you look at the compatibility layer, so actually it's just done in a way such that the existing OVM-based environment can use it just as an OVM version change. And that was our main goal and main motivation. We didn't want to put the burden on the VIP guys. We didn't want to put the burden on the SoC and affecting their schedule execution. And we've done that a lot in the past. We went through a lot of issues. So we wanted to avoid all of that this time and figure out how we can really create a long-term solution as we move from OVM to UVM to allow users to move instantly, but at the same time, give them the flexibility for any new code to start implementing in UVM when they get the chance to do so. So the code below shows the OVM package content, which, if you look at it, is actually derived from the UVM-based code. So if you look at any UVM package, you will see the green part. So this is when you open UVM package, you see this is the green part that gets instantiated. And then the compatibility layer code is split into the following files, which are red. We kind of took back the OVM macros, whatever we need out of that. So I'll go through a little bit of them. And then we took the UVM-based code that comes with it. And then this is where the bulk of the compatibility layer will sit, which is in that file. And then because we have a lot of legacy code, not only related to OVM, because we have legacy code that even comes from the AVM days that lives inside part of our OVM code. That's why we had to add a little bit of extra code on top of it to be able to enable that. Of course, the clean way we could have done and fixed the code, but again, that was proof of concept. We want to make sure that we can move any code without touching any of the IPs. So we brought back some of the legacy from the AVM as well. So if you look what's required to enable this compatibility layer, so there are a few things you need to do. The first thing, of course, you have to map all the macros. So you have to map the tick UVM to tick OVM. So if you look at some examples, so we define all the macros back, and all what they do, they actually call the UVM macros. So we did, for example, OVM do callback was just called tick OVM, UVM do callback. So OVM do callback exit on, it calls the UVM. And if there is any compatibility issue in terms if they change any of the argument, or they change anything, we can hide it in our OVM version of the tick define. And there are cases where they have done that, not with macros, but they've done that with some of the base parameterized base classes where we run issues. And because of that, when we redefine them, we have to change the way we pass arguments. So we hide all of that for the user as well. So this is one of the mapping that you are required to do. So you map from the UVM macros to OVM macros. The other thing, of course, you have to map the base classes. So for non-parameterized UVM classes, it's really pretty simple because you can do type def on all of them, and that's pretty easy to do. So you can type def UVM, for example, void to any OVM void, UVM root to OVM root, factory to factory. So those are the non-parameterized classes. So it's really easy to deal with. Just type def them and you'll be fine. But the biggest challenge becomes when you have parameterized UVM classes, which cannot be simply type def, because the language won't allow you to do that. So in those cases, what you'll have to do, you'll have to extend from your UVM equivalent and just pass the right parameters. If they kept backward compatibility the same, that's pretty easy. If they change backward compatibility, then you have to change how you pass the argument. So for example, you can define an OVM analysis port, which is parameterized, which extends from the UVM analysis port, and then you just new it and pass the argument. If the arguments are the same, as I said, if there is no change in terms of backward compatibility, you just pass the argument. If they do, then you'll have to change that argument passing as well. So this is how you deal with parameterized classes. So for non-parameterized, pretty simple, type def. For parameterized, you have to create a new class that just extends from the base UVM code. Enumerated types. Again, you have to map enumerated types. So to be able to use the UVM enumerated types, we had to type def them. So here we start type defing the UVM types as well. So we type def UVM, for example, active passive enum to OVM. And then we define the OVM passive to be UVM passive, OVM active to be UVM active. Same thing for verbosity. Type def all the OVM none to UVM, assign all the OVM none to UVM none, OVM low to UVM low, and so forth. And then for the OVM severity, same concept, you type def it, and then you assign all the labels to the UVM equivalent. So far we had to deal with macros, we had to deal with base classes, and then we had to deal with enumerated types. So with those changes, we were able, with this compatibility layer at least, we can get majority of the base OVM VIPs and environment to compile clean. But there was still a few UVM files that we had to change to make it 100% backward compatibility to our usage model. Some of them were required because some of the compatibility issues that were changed, or some of the deprecated API that used to exist but don't exist anymore. But a lot of those minor changes that we had to make in the file were really related to our use model, because we had a lot of code, legacy code that comes from AVM to OVM to UVM. So we needed to keep, again, we could have went and cleaned that code, but we wanted to have a proof of concept to show that we really can move 100% to UVM without touching any of our base code. So to do that, we had to touch a little bit of the existing UVM code. And as I said, some of it were required because of deprecated APIs, but most of them were related to our usage model. So I'm going to go through a little bit of examples or some of the minor changes we did. They're not much, but they were necessary, and they're not going to touch over all of them. But there's not much that needed to be changed, just minor changes. So for example, we had to add the pre-run call and call it from the start of simulation in OVM components. So pre-run, as everybody knows, has been deprecated from UVM, and the API does not exist anymore in an OVM component. But in our legacy code, I said some of it are related to our usage model. Some users are just overriding the pre-run and actually calling super.prerun. So we had to bring it back in. So we just defined pre-run in the UVM component and call it in start of simulation to kind of mimic exactly how we had in our legacy VIP. Some other stuff we had to add, for example, is we had to add the OVM report star functions into the UVM component because most of them are gone. So we went ahead and we redefined those because we are using them in our legacy code. So for example, OVM report info, we have tons of code that uses that API, so inside any OVM component, so we had to bring it back into the UVM library. UVM factory, so same thing, we have a lot of legacy code that use the create object into the UVM factory, so we had to bring that back in as well. So we defined the function UVM create object, we brought it into the UVM package again, and then we added to the UVM factory. And also for example, set instance override function. So we use that a lot, and some legacy code is using this, and it's deprecated from the UVM, so we had to bring it back into UVM factory. So those are some of the minor changes that we kind of had to do. So, and of course, one thing which is required, I'm sure you're going to see in a lot of OVM code, everybody uses that, not only our usage model, is, of course, the OVM test stop. So we had to add the OVM test stop to UVM globals. So we just define OVM test stop to be of UVM component, and then in the UVM globals, of course, and then we have to assign it back in the UVM root to UVM test stop. Because we use a lot of OVM test stop in our code, either people to globally turn off stuff or to globally affect the whole simulation or verification environment. So to be able to mimic the same behavior we had in our previous VIPs is just define it to be a UVM component and just assign it to UVM test stop. After doing all those changes, that bring me back to the results. So we were able to successfully migrate an OVM SoC, which was purely OVM-based SoC, to UVM using the compatibility layer. There are about 25 plus VIPs, and they have really very complex bus interfaces like OCP, HB, AXI, and they have a lot of IOs like PCIe, USB, and SDIO, etc. And we had to add more code in our compatibility layer, as a few of our legacy IPs are even dependent on OVM compatibility layer. And that's what I mentioned in the beginning. It would have been nicer to clean that code, and we don't have to bring also as well to the OVM compatibility layer. But we wanted to, again, proof of concept and make sure we don't need to touch any of our VIPs if possible. That's why we brought as much as possible from the AVM compatibility layer, and we added a little bit of much code to enable it. We managed to get all our level 0 regression tests passing, which consists of 100 plus tests. It almost took us 3 person weeks to enhance the compatibility layer, and took us almost 2 person weeks to run regression and achieve the same result as the reference and get the same behavior. During that process as well, we were able to file several Mantis items on UVM source code based on issues and bugs we observed when doing that migration. If I take a simple example, for example, the print topology was scrolling in UVM compared to OVM that was when we were doing that. And we filed as well a few simulator enhancements that we needed to enable our compatibility layer and our usage model as well. So summary, ideally, it would be nice to start from a clean code and not create a compatibility layer and everybody start fresh, but that's not reality. It's not possible. It's very hard to do that in a very dynamic environment where you have SoCs. You have maybe 10, 20 SoCs running at the same time, all of them getting VIPs from all over the places, from internal, from external, and you have several groups that are providing VIPs for you, and all of them are already using OVM. So in our case, it's not possible because of the amount of OVM code that we have, which need to be converted and tested. Converting it most of the time is not a big problem, but making sure that all your regression tests still passing is the biggest challenge, and to ensure everything is still working. So, and because we have tons of IPs that we get from all over the place, whether it's internal or external. So it is not an easy process. At least for us, it will take us years before we get there. But we wanted to figure out how we have a transition or provide a long-term solution that allow us to move forward without having a huge impact either on our resources or even on our execution schedule. So having that compatibility layer, it enables an SoC project to move to UVM when they decide, when they have the time, and they think it's the right time to do so, and therefore without any effort or impact on their execution schedule. And this way, any SoC can just start developing new code in UVM, and then they can take opportunistic approach in converting the old code as their intercept and their time schedule permit.
All right, I'm Richard Sim. I'm going to talk about the reusable verification testbench architecture supporting C and UVM mixed tests. A quick introduction about my team and the project we're currently working on. We're working on 3G UMTS WSDMA modem core that goes to an SoC design. The chips goes into the femtocell base station. Currently, we have 7 verification engineers in the team, and the team spreads out through the New Jersey, Boulder, and Bangalore, India. And we have 4 design engineers, and they are located in Boulder's office. We're gonna have a quick introduction about this presentation and some background information, and we jump straight into the Testbench features and talk about this Testbench architecture overview. And we're going to talk some more about the challenges when we build this Testbench and the solution to go along with that. And then we have a summary and a Q&A session at the end. So the UVM will be the ultimate methodology for design verification. I guess everybody knows about that. I don't really have to repeat that. Not only because it's the latest and greatest technology, but we also have a strong EDA vendor support, and they provide all the verification IP that we can quickly drag and drop into the design verification environment and quickly build a test bench. The biggest advantage in the UVM for me is that the verification IP and the test sequences can be reusable for different platforms or different design generations. But in many test environments, C was primarily used for the testing. In our application, we have 1,000 lines of C code, and those C codes were evolved from many design generations. There are hundreds of scripts already written to support a C test, to generate the C data object, and we link that into the simulation. And those C codes are recognized as a golden regression suite. But one of our goals is that we want to migrate all the C test code into UVM sequence. But that's not an easy job. It cannot happen overnight. So our goal is that we wish to build a UVM test bench that enables us to reuse all the verification components as well as the C and the UVM tests. So test bench features. So the test bench I'm going to introduce here, it allows us to reuse C and UVM tests in different verification platforms. This is one of our goals, of course. And we will talk about how to run this C and UVM tests simultaneously and then reliably. So when there's multiple threads try to access the same interface at the same time, sometimes there's a race condition will happen. There's some additional work need to be done in the test bench to take care of this. And then we'll talk about which part of the test bench can be reused for different generations. And then we have a couple slides to touch the register layer integration. This test bench is architected in multiple layers. We're going to go cover this from bottom up. The bottom is, of course, our design of the test. And above that, we have this UVM agent layer. This agent layer, we have a XI master agent and a slave agent. Each agent here has a sequencer driver and the monitor building there. Usually it's provided by the EDA tool or the VIP vendors. And this talks into the design and the bus interface at signaling level. And above that, we have this generic transaction translation layer. The purpose of this layer is try to translate the high-level generic transaction item to the bus interface-specific transactions. So in this case, we have these 2 boxes that map to the generic transactions from high level to the XI transactions. I named this GPV and GST. Don't be bothered with these acronyms. We'll talk about that a little bit later. But for now, you can think these are just generic sequencers that will handle the generic transactions. And this translation sequence are in here, and it basically does the translation job. And then above that, we have this virtual sequencer. The project virtual sequencer, it holds all the handles of the sequencers that will be used in design verification environment. And then it also holds the handle of this top-level interface, and we'll talk about that. And the actual sequencer is instantiated at this level in these 2 boxes. But this is a project virtual sequencer just holds the handle of that. That's why it's called virtual. And above that, we have this C to SV translation sequence. You know, the test bench has to support a C task. So this layer is basically translate the C transactions to generic transaction. And so you can see we have integrated the register, UVM register layer at this level. And it has a hookup to this TPP sequencer. And above that, we have this top-level interface. And this top-level interface, we define a set of generic tasks. That's the tasks are defined in system Verilab or UVM. And then we export those generic tasks to this C function. So the C function, in there we can create a task and we can use those generic API tasks. And then once the task is available, we can import that to this top-level interface. And then we can fire the task from the UVM sequence. And also here we have these two little boxes here. It's called GPP to C interface and the GST-C interface. Basically, these two boxes is our sub-interface that instantiate inside this top-level interface. I call this structure as interface of an interface. So basically, there's a synchronization event and built in there to handle the handshaking process between C and the system Verilog domain. And also, there's a semaphore allocate for each interface. So when multiple threads try to access the same interface here, there's a race condition could happen, but the semaphore there is set up there, so you can only take one process at a time to make sure the race condition is taken care. And above that, we have this UVM tasks, of course, and the C functions, and we have a set of a UVM register test sequence. The test sequence while talking to this UVM register layer and pass it on the transactions. Challenges and solutions. We have 3 topics to cover this. So usually, the C task is programmed with the API task, but for the UVM test bench, when we try to create a test sequence, we use these macros, 2 macros. It's like a do UVM do with, and do on with. But the caveat is that we cannot use these 2 macros in C. And we used to create a generic API task, and then we create a task with the generic API task. The test will look more consistent and a lot more cleaner. So in able to reuse a C task in the UVM test bench, we have to figure out a way that we can try to map the C API high-level task to the UVM do macros. The way to do that is we can define a UVM task there, UVM API task, and we can specify some constraints either in the argument line, either in the arguments or inside the API task. We have an example to show that. So usually this is the transaction generated from the UVM sequence. So we use this UVM do macro, and this is a sequence item and associated with this XI master sequencer. And then we specify this some constraints here. In this case, we have this address and data and command type. The command here we specify as XI incremental write command. And we also specify some other default constraints here. But then if we want to do the API task, the equivalent API task just with like this, it's only one line here. So here is we call it the XI master write, and we pass the address and the data. And the way to implement this API task is that we define this task, and we create a sequence item. And then we randomize this sequence item with some constraints. These constraints are just similar to the UVM do macro when we create a UVM transactions. And the address data is passing from this the command line interface. And the XI incremental write command is implicitly specified by this task name. And then we send these transactions to the sequencer. So next we're going to cover how to reuse this high-level C in the UVM task and which part of the test bench can be reused. So if we want to make the task portable, we should program the task with the generic API tasks. So in our example here, we use a GPB and the GST transactions for tasks. The GPB here stands for generic primary bus. Basically, it's usually mapped to your primary bus interface, and you can access your register space, or it's usually doing the front door register transactions. So in our case here, we have this GPB write task. It maps to the XI master write at the bottom, and GPB read maps to the XI master read. And the GST stands for generic slave transaction. And usually in a slave model in the test bench, we sometimes we want to do some backdoor transactions to access the memory contents. And so we have this GST backdoor write task that maps to the XI slave backdoor write, and the backdoor read maps to the slave, XI slave backdoor read. So we can also use this API task to preload a memory image or dump a block of memory contents. So the GPB and GST just generic term I used in the example just for demonstration. You can name it whatever you want. And if you have more than one register interface, you can probably name that GPB1, GPB2, or GPB3. And they could be mapped to HB or XI or some other proprietary interface. And the GST task, you can map that to an external DDR memory to some backdoor access there. So here's the task sequence look like in the UVM. So we have this GPB write, GPB read, and then we can do some idle, we can do some delays on that interface, and we do some backdoor rewrite transactions. And this at the bottom of the UVM agent layer, this task can actually call with this XI master write, XI master read, and a slave backdoor write and read. Also, we can make the UVM and the C task identical. So one of our goals is that we want to migrate all the C task code to UVM sequence, but it's just too much work. We cannot do that in one shot. So the way is that we try to make the UVM sequence identical to C tasks. So in that case, we can easily create a script and just change to translate all the C task into the UVM sequence. So the top, the blue box here, this is a UVM sequence, and at the bottom is the C functions. And this task they'll look the same. But one thing is that we are able to use the UVM macros, the reporting service macro, in the C domain as well. We'll talk about that in the next slide. We have quite a few reporting macros. Those are like UVM info, UVM warning, error, and the fatal message service. This message service macros we can specify the verbosity level and the severity for this macros. And when the message is generated by this macros, it will tell us where and when this message comes from. It's a nice feature in the UVM, but we want to use the same features in the C. And the implementation is pretty straightforward. And so in a system Verilab file, we define this UVM report info function. And inside this function, we actually call this UVM info macro. And just the regular usage method, we call the UVM macro. And then we export this function into the C domain by using the export DPIC command. And then in the C file, we define the verbosity level in exactly the same way as the UVM defined. So we have the UVM low, medium, and high. They were defined as constants. And then we call in the C file, we define the C macro, and we call this exported function. In this case, the UVM report info, which is defining here. We're talking about how to reuse the high-level verification components. So in our design, later on, if we change the bus interface on the design, of course, the UVM agent layer, the bus model need to be swapped out and replaced with the different models. And also the translation sequence here need to be changed. But everything outside of this bus can be reusable, just including all the test bench components and the translation sequences, as well as the task, the C task, and the UVM tasks. The next one is the UVM register layer integration. So nowadays, the UVM register, the register testing is one of the common requirements for signing off the chip tape out. And there are so many ways we can generate the register models, either with a customized script or some EDA vendor tool. They provide some script can help us to parse the software menu and generate the IP exact format or the text file, and the tool can continue again to generate the UVM register model. And when we talk about register model, we're always thinking about the prediction mechanism. How the model works is that we try to keep a copy of the register value that's updated along with the design. And the prediction mechanism is used to try to keep in sync between the register model and the design registers. And there are three prediction methods can be used. The one that we're going to talk about is called explicit prediction method. And so this register model will be updated under two conditions. And when the first condition is that whenever the register operation is issued by the register sequence, and the register model will be updated immediately. And this prediction mechanism is called auto prediction. And another prediction method is called passive prediction, which means we drop a bus monitor in the test bench, and we monitor those bus transactions. Whenever that happens, the transaction happens, meets the protocol requirement, we generate a transaction object, and then we present that to a predictor. That predictor will update the register model. And so actually the explicit prediction mechanisms combine these two mechanisms. We want to support this prediction method, and this additional work needs to be done in the test bench, and so that we can reuse the register sequence and the predictor. So here's the picture of the register layer integration, and this level is a UVM register layer, and everything below this dotted line here is identical to the first picture, which is the overall architecture overview. And above that, we have this register sequence. So in this predictor here, we have to specify this, I call this a rec to GPP adapter. This adapter is actually installed in the design environment, but this predictor just holds a handle of that. And there are two functions that we need to be defined. And the first function is called rec to bus function. So this function works is that whenever there's a register operation issued by the register sequence, you update the model and call this function. And this function will translate the generic register operations to our generic sequence item and pass down to the lower layer and talk to the design. And then whenever this bus activity is captured by these monitors, and the monitor will present that transaction to this adapter again. And then this bus to rec function will be called, and that will translate a generic transaction item to the register operation transactions, and that will update this register model. So in our applications, we are able to reuse all the test sequence verification IPs and in multiple test benches. And at core level, we have this core level test bench, and we map the GPB and GST transactions to QSB, XI master, and the slave. QSB stands for the Qualcomm System SoC bus. Qualcomm SoC bus basically is an addition to the standard XI master, but we support some other out-of-order transactions and support some other processor features. But we also have multiple block level test benches. And the GPP and GST transaction were mapped to the proprietary bus interface. And then we also have an emulation platform. And we built a test bench in order to run some simulation there and to debug to support the lab debugging. And the GPP was mapped to the HP master, and the GST was mapped to the off-chip ZBT memory transactions. And we have run so many thousands of regressions with this test bench architecture and with different multiple simulators, and it's really running pretty stable. So the last point is that the test bench architecture extends the reusability beyond the scope of the UVM technology and also across the C and the system language boundary.
I'm Asad. I'm a design verification lead at Texas Instruments. So this presentation is very unique from perspective of not just today. I've tried to cover a lot of ground here from perspective of where we were several years back and where we are today. What I've tried to do is I've tried to give examples in here to make sure you understand from where we were, how we use UVM to address a our problems and how we actually implemented solutions. As John mentioned at the start, this is not an expert forum. I've tried to give as much examples as possible, but they're not like detailed. So if you have any questions or whatever, we can always, talk offline or whatever. So what I'll be talking about today is what were our challenges before we started implementing any available solutions from the industry. This is going back several years back. How we actually use the adopted solutions, and even using those adopted solutions, we had roadblocks for those solutions. I will talk about some key issues that were addressed and how we actually use UVM to address those issues, and I will go into details of those. One of the interesting things that we have gained leverage from UVM is an AMS simulation environment. And then I will give some conclusions and give opportunity for question answers. Some of the challenges that we had before, a lot of the verification environments that we were using, they lacked constrained random stimulus generation. They looked as if we were using patched environments together, and there was no uniformity towards any verification environment we were using. But there was no functional coverage driven methodology. We didn't have automated checking in place. We had VIPs, and these are the days very far back where there was no provisioning for integrating those VIPs in our environments. And then biggest challenge that we had was we had block level test benches, but there was no way to go back to top level and use those stimulus at the top level. And at the same time, we had so many directed test cases that you would open an environment and you would see that there were thousands and thousands of test cases, which was a management nightmare. And you do not want to do that when you're writing your verification environments. So what we did, we started going in the industry. We started with Verilab, of course. We did use Pacman, we did use VMM, we did use OVM, but for a very small time. But what we saw that even with these adopted solutions, there were problems somewhere or the other places. Like, for example, in some cases, there was not full LRM support. Some of these solutions were language specific, and they were not open source. So if somebody who wanted to go debug, it was an encrypted solution. Now we are seeing that they are open source. They were very simulator dependent, so if you were trying to go from one simulator to another simulator, we had compile issues and whatnot. One of the important things that was missing in a lot of these solutions was the base class implementation. And this is where we spent a lot of our time coding and giving support for those base classes. One way or the other, any solution that we had implemented, we had always had to go and write a wrapper, going from one implementation to another implementation. VIP solutions were there, but they were not standardized. Everybody was using their own kind of methodology, and if you were using a VIP in our environment, it was not compatible. So we had to go back, write wrappers to address that. And then lack of phases. Some had phases, but today you will see in UVM there are so many phases that you can use during the runtime. So some of the key issues that we were facing, every time we were writing a packet class, the test writer was actually going and rewriting a lot of code, and there was no automation built into it. End of test issues, this is a very trivial kind of thing that when you look at it, but for us it was a big problem because every time a test was running on a regression or an individual test, it was just sitting there running for a long time. We could never predict when that particular test would end. And then inconsistency in test development. As I mentioned, there were several directed test cases, and there was a lack of base test case or a uniform way of writing a test case that a test writer could follow. This is an example that I've taken that we faced. We had a DUT with multiple interfaces, and we had a challenge of controlling several interfaces in that DUT. And we used callbacks in that, but it became a nightmare when we implemented that solution. I'll show how we use UVM to address that. All of you who use UVM might have seen, or use verification might have seen that you have several BFMs and monitors available from legacy verification environments. In our case, we had those BFM monitors, but there was a lack of scheme to go and generalize them and use from project to project. And this is another issue that we have faced, a lack of debug messaging support. Every environment that we use, we had custom debug messaging support that was implemented there, and that made our simulation logs and debugging really hard. Then I'll touch on some miscellaneous test bench issues from implementation of channel data processing, how the phasing came us for help, and some extensive register model coding that we were doing that was reduced by using UVM. All right, so packet class, on the left, I've tried to follow left is before, right would be after. At first, we were writing classes with all these packet classes, and in this red, this is the code. The test writers or the test bench implementers were writing that code themselves. There was a huge room for here to do mistakes. For example, if somebody missed a particular member function here, and they were trying to do a deep copy or, or display somewhere, they were always going and debugging this manual amount of code. But when we went to UVM, what we saw was that there is always a built-in automation. John gave some details here. We did see those pitfalls in our side in implementation here, but in all, the amount of coding that we were doing here was reduced by using these object utils here. And our implementation became simpler from perspective of debug. End of test issues. The most logical way to predict an end of test is when all the interactors, your stimulus drivers, your collectors, and your scoreboards have completed processing. So that would be a true end of test. But in our case, we had complex environments, and what we saw was that we were trying to write our own detection of end of conditions, and that became very complex. We were always out of sync. So we also use some callbacks, but test writers or the Testbench writers actually miss those callbacks and registering in the build class. And even in that case, you would have a test case that would hang, but you would never know, is it hanging because of your end of test or is it really hanging because of an issue? So we went ahead and started adding drain times or delay times in there. But then when we went to RTL or gate level or AMS simulations, because of the nature of these simulations, that drain time is not a global way of addressing how to end a test case. However, when we go to the UVM's raise objection, drop objection, or to the UVM test done was followed very diligently in everywhere in the test bench. We added those in the test cases, we added those in our sequences and our virtual sequences and any UVM component blocks that were designed in the test bench. If we had our own phase that we had designed, even there we used the raise objection and drop objection. Then you have the opportunity to use the global stop request. You can add the timing in there and terminate the test if you want. And if you want to debug all this, there is a phase done display objections that you can use to see which objections are still up or which objections are dropped if you have a hanging test issue. So a lot of this automation comes in, built in. So you are not leaving all that to a test writer or test bench creator. Inconsistency in test development. Test writers were writing their own code. I'll take an example here. They use a program block and they would pick up a spec and they will start writing a test case. Here I've taken an example. Somebody went in and they wrote a test case where they initialized the test case to a bad address location. Now, they didn't know that they were doing that, but they started generating the traffic and they expected that bad location or that location would return a non-zero value. But by default, that was always set to a 1 and they got a false pass. So a lot of these test cases would pass, but there was no check in place to go and see how you addressed a true pass. So we would see in waveforms and we would see in other cases where somebody who did not do this would catch this problem. But the problem was that all these test cases became like humongous test benches in themselves. When you go to the UVM side, the UVM provides you a UVM test class. What we did, we created a test base class and we added all the common code in here. And the test writer would not go and change this code. He would go or she would go write this test case right here in the class, in the test case, and hence, they would be less prone to doing any kind of a mistake like this. And the biggest advantage is that our test cases got a uniform look to them. There was a template test case that everybody was using. And if your specification changes, you're not going and changing your thousands or hundreds of test cases that were written here. You just go and change one particular place, all the basic configuration. And, you address that. So we got consistency using this UVM implementation. Now, this is an example where we had a DUT where there were 4 interfaces, and at the time of the solution we were using, the interface A could configure, B, C, and D interfaces could be either read or write interfaces. We saw that the callbacks could be used at that time to implement or address this challenge. The idea was that there's a lot of interaction between these interfaces. One has to wait for the other, and the goal was to actually go and do full and empty conditions, and a reconfiguration could also happen while you're doing that. So we did implement and address that using callbacks, but it became a management nightmare from perspective of maintaining those test cases because, you can see there's so many permutations here and, people were writing directed test cases and they started growing, in number. So I've taken 2 examples just to give a little bit of, insight in here. First example is where we configured the interface C and D to be both read and write, and interface B was configured to be write. So you go and configure the interfaces, you fill up your DUT, from either C or D, and then you do reads from the same interface to make it empty, and then you can use your interface B to write again and C and D to empty. So idea is to do a full and empty in 2 iterations. Another example that I take here is the reconfiguration. So, same case where C is write, D is read, B is write only, but in doing the first full and empty, you can actually go and reconfigure from interface A again to make B a read and D a write only. So there were several test cases. If you go and open your test case directly, they were addressing one after the other, these kind of solutions. And it was looking at a rat's nest, basically. There were like so much stuff in there that you would not know what was going on. So just to give an example, a test writer would go write a program block. They would have a write task, a read task, they would register their callbacks, and boom, one test case. But when we went to UVM, we were able to use sequences, nested sequences, and the concept of virtual sequence to create a very generic for loop. The test case came down to just this colored portion right here. We were able to create constraints in our test case where you could tell the test bench, do you want to reconfigure or not, true or false? How many iterations do you want to do of full or empty? What is your first order of doing full or empty? What is the second order of doing? And what is the configuration? And we actually use ranges in here to use these enumerated types to actually go and randomize test after test. And there was a number of 300 plus test cases here. We reduced all of them here to just 10 test cases and ran over multiple random seeds and were able to do the same thing, coverage from coverage perspective that was done in this case. So BFM monitor reuse issues. Now, from the perspective of BFMs, we have done so many protocols. We go from one protocol to another protocol. What you see is that you're always using a BFM. Now, our problem was that we were customizing the BFM from perspective of every project. Testbench writer would take a BFM, drop down the top level, and they would just start customizing it from perspective of your pins. And the problem was the test code that was written, all the monitor code was embedded inside the test cases, and everything was scattered. There was no way you could actually go and say that, okay, if I'm going from project A to project B, how can I actually reuse everything in one day, or without going and extracting all this information? So using the UVM, we followed the methodology by declaring our drivers, putting our BFM tasks or whatever not inside drivers, having a master agent, having configuration, and the slave agent with the monitor code in here. So we were able to encapsulate our legacy testbench code in a very reusable plug-and-play format. So when we went from, let's say, for example, in case of USB, we were able to use this from project to project without much changes at the top level. Debug messaging support. Well, in our legacy test benches, and a lot of these examples I'm taking, they go way back also. So I'm actually giving a full depth of insight here. I've taken some examples here where we were using display statements to actually go and print what was happening inside our test bench. The test case writers were actually going and writing tick defines to actually define their own warnings, errors, and debugs. It was a lot of code being written to do the same thing over and over again. And what we saw was that, there was a huge room for mistake here. Somebody interpreted the error or the warning in a wrong way, then you are actually just leaving that whole thing to this implementation. When you go to the UVM, you can see here that not only that we were able to design our environment methodically, and here I take an example of our assertions block, our scoreboards and monitors, we were able to use the UVM medium, low, and high verbosities to actually turn on and off the log that is generated in our end of elaboration phase. And so for those who have used the UVM, you can do all that by embedding this verbosity inside the tick UVM info. And this code can be anywhere, and they have a priority where you can actually use that priority to print these. Not only you can do it during runtime through a test case, you can also launch this medium, low, high from your command line also. The biggest advantage that comes out of this whole thing versus this one is that, while you use this warning, error, and fatal, macros, you will see in the next slide also, you can control your top level pass and fail also. Using the UVM report server, considering the tick, fatal, and the error counts that you can actually add, you can go and add a code just like this, and you can, when your simulation hits the report phase, you can actually report if it failed or passed based on your checking. The advantage here was that we were able to use this report server and customize it according to our own print statements. So here it comes with a default printing, but we were able to add our own logical kind of printing where you can do grep it, or if you want to look at it exactly from perspective what you want to print. Another advantage from debug support is, in our legacy environments, we were never able to look at the hierarchy of a test bench. Either we were able to look at that hierarchy inside the waveforms, or, we had to add other kind of support. Here you can use this .sprint, and, you can control the depth of how much hierarchy you want to print. And, the whole test bench at the time, wherever you want to print will be printed. You can see exactly what is it configured. This is just a very small snapshot, but, you can print the whole test bench, everything in there. Some of the miscellaneous test bench issues that we saw over time. When we were using the channel implementation, the test bench writers were writing a lot of their custom code. They were pathing down from one block to another block. They were doing A.B.C. If something happens, then do this. A lot of code was just gathering into components, But when we went to UVM, we were able to use the TLMs, and TLMs gives you like port export, your analysis port. So if we wanted to transfer data from, let's say, scoreboards or a collector at the output port, you can use an analysis port and send that data. So basically use the built-in automation that's already there. Another challenge that came in was how do you synchronize your components? We have a lot of VIPs that run in our environments. And the biggest problem that we were earlier seeing was that how do you synchronize all these VIPs? We'd use callbacks, but we also used events. But the problem was that if you're not using an event or callback properly, then of course you're stuck in that debug loop. One of VIPs might have finished a reset here, and the other is still in the reset. And using this customized approach would create confusion. You go to UVM, you have phases. The run phase has a lot of these built-in. You can also create your own phase, a custom phase, and whatever you want to do. Let's say in a configuration phase, everything gets aligned in that particular phase. So continuing on the test bench issues. Now this is a very interesting thing that all our test bench implementations, we had close to like thousands of registers in our DUT. Earlier we were doing a lot of coding. We were just actually going and writing if-else statements, and we were writing all that code ourselves to do compares and whatnot. What happened later was that, and this has been appreciated a lot internally, we have been able to create like an Excel sheet. We take our whole test bench register space and implement it in an Excel sheet, and then using the Spirit consortium scripts which are out there, we're able to process the Excel sheet, use that JavaScript, and dump out a system Verilab code. So this is all push button, and it comes with coverage implementation. There are cover groups already implemented in here. You can extend those cover groups to add more functionality, but the idea is that there's the user mistakes have been minimized to the lowest category, and everything is now automated. And there are some other advantages with this also, because in our case, we have several revs of specs that come out one after the other. So we are not sitting there doing manual coding. It's just a 10-minute process where we go and update it to the new spec. Okay, this was the biggest advantage that we saw from perspective of UVM. Before using UVM, we had good implementations, but we were never able to use that in our Virtuoso or ICFP environments. Either we would good compile errors or we would good partition errors and whatnot. So we had to resort to writing our Verilog EMS directed kind of test cases. That never changes, of course, but the methodology around it was all manual. What you would see is that the people were writing directed test cases, and then output logs were getting generated. They had their own custom scripts to process it. They were looking at the waveforms, and everything was manual. So there was no concept of actually automation in here. But when we went to UVM, as you saw, the test bench that was already designed as a plug and play, we were able to instantiate this test bench in our Virtuoso environment, make it a symbol, and then all we had to do was create a glue logic here, where we just translated the logic elements in this particular side to electrical, and we were able to use end-to-end test bench with full packet traffic, full checking, everything. So you're going from basically no checking, no automation to full automation checking right here. So there's some technical contributors. If I draw the conclusions and looking at other presentations that have happened so far, in our case, UVM cleanly addressed our critical issues. We were stuck in several problems from perspective of vendors, we were compilers, whatnot. All of them were actually making us either go towards slowdown, or a lot of time was getting used to write wrappers and code rewrite. All that was reduced, because of all the available automation in place. The UVM development goals do align with our verification strategy. We have seen that all the new releases that are coming out, they address all those functions and LRM supports that we do need. We did start from the early adopter version, and what we have seen is that there was a recode effort that was required from going from this to 1.1. We have not migrated to the latest 1.1, but that's to do. But what we saw was that there was a lot of guides available, and we were able to use those guides and translate from 1 point early adapter to 1.1 easily. So in conclusion, if you look at the UVM implementation, getting started was very easy. There are a lot of trainings available. John made a point, yes, you cannot just take a training and, be an expert in 3 days. But a lot of our test bench creators, they know object-oriented methodology. But, using these trainings 2 to 3 days, they were able to create complex test benches within no time. What we found is this is the biggest advantage that we have seen. A lot of vendors have started following this UVM. And now we can actually go off the shelf, use a VIP and integrate in our environment. We don't have that problem, though this VIP is in Veras or this is in E or whatnot, and you have to write a wrapper around it. So everything is coming with a SV interface. So we are today using the UVM actively in our digital and mixed signal verification, and we do plan to use it in our analog verification. In fact, effort has started already, where we're using port-based checkers, automated checkers in analog cells.
Just a word of caution here. This back again here is not because we got to UVM and changed our minds. It's because, as you'll see in the presentation, we have a slight requirement in some of the clients to do some backporting from UVM. So this is where we stand, mainly in the current client I'm in at the moment, but we also see this situation in a lot of our clients, and I guess a lot of people in the room here. We've been working at this client extensively in OVM for the last couple of years. We've got a lot of projects, a lot of derivatives, and we've built up quite a family of verification components in the OVM. There's a goal in the client to move towards UVM. It's the latest thing, it's the best thing, as we heard in the previous presentation. It's also much better, moving forward, much better supported with the different tool vendors. And also, of course, with Synopsys much more on board and such like. We as users have a better choice. We've got the three big guys out there to choose from. At some point, to get UVM off the ground, though, we do need to do a migration. And this is kind of where we are. This is the kind of now line, right? So this presentation is a little bit about the case study, and it's different conclusion or different results, if you like, from the migration case study we had earlier. So I think you'll benefit from both presentations. Of course, as we move forward in UVM, we're going to be creating UVCs for new protocols and the new chips. And some of these, at some point, because in this client, OVM is definitely not dead. It's not an immediate switch. I think with 2 or more years legacy, very many verification components in our library, it's not practical from the project point of view. We also heard this from the earlier presenter. The actual project owners are kind of saying, no, it's great, it's fine, it works, we can tape out. We're not prepared to put the projects in jeopardy, but we do appreciate that you, the methodology guys, get everything ready so that we can make a switch, and in particular, we want new UVM, new project starts really to move directly onto UVM. But also, we have this, because these projects, new projects are ongoing, and the existing projects are not dying, we have to take effectively born UVCs back into the OVC world. Now that affects what we're going to try and do for the migration process, specifically for the translation process. Now this green dot here, I've shown way back here, this is the UVM reg. We're already using the OVM version of the UVM reg, and we have been for well over a year and a half. The goals, remember, we've got to support these ongoing OVM projects. This is where most of these OVCs are live. They're getting bug fixes, feature enhancements as we go through the derivative chain here. And we need to provide them because we're not going to start UVM from scratch. That's just not feasible. But we don't want to be locked into OVM forever. Now, we did a deliberate 2-stage evaluation here, partly because we knew our starting point. This is also different from the previous presentation. In our case, we had clean family, not just one OVC, but 4 projects worth of OVCs. They're all derivative projects, so they're all quite related. But they're clean OVM 2.1.2, so the latest version of OVM, slightly later than where UVM was branched off, but this OVM 2.1.2 has a little bit of the improvements from the earlier UVM brought into it. We have absolutely no legacy. These OVCs in this case were constructed from scratch. And in addition, it was the same team that did most of this. Or if it wasn't these guys, they generated coding guidelines to help the other guys generate the OVCs. Now this is important because I think this makes it easier, right? It's sort of maybe the other extreme from the earlier presentation on translation that we had earlier. Because in our case, our scripts end up being really effective because we have a family of clean OVM 2.1.2 OVCs. But they're less general purpose. If you've got some AVM legacy in there, it won't get automatically converted, for instance. Now, our first stage evaluation was really just to try it. We took a whole project with 13, 14, 15 OVCs, but top level project. And we went through basically the same flow you see on the great pages from Mentor and the Verification Academy stuff. I'll show a slide on this. But the goal was just to see, was it going to work? Was this concept that I had, that the translation was really going to be straightforward in our case? Was it flawed? Did I miss anything? So that was the goal of the first attempt. And the goal of the second attempt was to try and optimize it so that we could achieve all our project goals that I showed on that first slide, especially the ongoing development of stuff in OVM and the capability, at least in concept, to be able to take some of these UVCs back into the live OVC project. Now, the first stage evaluation, I'm calling it early UVM translation, but it basically follows more or less the flow in the Mentor Academy thing, but with a little bit more automation. And specifically, we're auditing our OVM code to check if there's any strange things in there. Then we do a translation to UVM. Now, at this point, you can run with UVM. The next stage, though, is to convert to UVM style. So instead of using the older style, the OVM run phase still exists in UVM. There's something called run. But this means, well, we should be converting that to be run_phase with the phase parameter, etc. The objection handling and the configuration database has changed a little bit. And virtual interfaces are an interesting topic. I'll come back to them later. And of course, there's new UVM features. There's some stuff that's deprecated in UVM that used to be in OVM. There's improved message macros, improved command arguments, and there's this new UVM register model. Now, as I said, there's a certain level of automation here. We managed to generate simple scripts to detect most of these things, so it was an auditing process. So for instance, this first one here, it's really just an automatic version of, there's a file that gets shipped with OVM that's called deprecated.txt. Yeah? And this is just a script that goes through your whole code base and says, oh, you might have a problem here, but it's just looking for patterns. It's just grepping effectively. Yeah? If you want to fix them, you have to do it manually. So that's what this means. Automatically detected it, but you've got to manually fix it. Some of them, it's doing automatic in both cases. You can see the way I filled the table out there. The key thing here to bear in mind that, as I say, this flow works. You can successfully run. We didn't run full regressions here, but we certainly ran lots of tests having gone through the flow here. And also, by the way, this flow didn't take forever, It was a few man-weeks of work to take this whole project from, admittedly not from a beginner, from an experienced person, but it wasn't a huge amount of effort. But in this case, for our use case, there's too many red X's down in this UVM part. This is all UVM code. And the problem with that is that our verification IP lives in OVM, the live version, the updates and everything are still getting done in OVM. So we can't afford to manually do conversions every time we want to release a version of a verification component into the UVM world. So really our goal here is to find a flow where we can push all these X's, or most of them, let's say, up above that line there. The idea being that once we, in this case, and this is the key fundamental difference, I guess, to the methodology that was mentioned earlier, in our case, we want to fix these things once in the OVM database. We already have clean OVM, and we want to make it better prepared for a translation to UVM. Yeah? And pushing stuff back to OVM, there's two real categories here. The first category is, well, there's stuff already in our OVM source. Now, we tidied it a little bit, because some of the OVCs maybe were not as ideal as the other ones. But nonetheless, we were using objection handling. We weren't using these funny global stop requests and all that. We were extensively using objection handling. We just tidied it up. We were already using these improved message macros rather than the function calls. They're in OVM 2.1.2, so you can use the OVM versions of them already. And we had already started using the UVM register that was backported to OVM as soon as it became available, whenever that was, 1.5 years ago or something like that. Now, in addition, there's a couple of key improvements. The two main ones I'm going to mention here are the interface configuration. These are key improvements that we can do in OVM to prepare it for UVM. Yeah? The interface configuration and the deprecated sequence utilities, which we've heard about a couple of times today. I'll just go through them as examples. Now, the interface configuration is dead easy in UVM. for me, the penny only really dropped how I could do it better in OVM once I looked at UVM and thought, how could I make that translation path as easy as possible? In UVM, we can literally set a pointer, a reference to the real interface using the configuration database. I don't get into too much details here, but the code looks like this. You can call the configuration database and you can parameterize it. So this reference to the virtual interface is in here, and we could call that directly. There's an equivalent get in there. You've probably heard of containers to do a similar thing in OVM. And that's basically what we did here. As I say, for me, it was kind of, not only can I use a container here, but I can do it in such a way that the translation is easier. And that involves making the methods very similar. That was really all we did. There is an OVM container that was contributed to OVM. This isn't it. This is the client-specific container. But the only real difference is that we thought, no, there's no point in doing the set and get the way they were getting done on that contributed OVM container. We said, let's do them simpler for the purpose of doing translation. And I think you can appreciate from this code, it's easy to do that translation automatically. And this could be a double-sided arrow. It's easy to go back again as well. Now, the other example I said we'd go through was the deprecated UVM. The main thing that's deprecated there from the user's point of view, I would say anyway, is the sequencer and the sequence utils. In other words, the old way of doing the OVM-style sequence library, which I guess somehow was inherited from Specman, from its look and feel, but it's not really a practical user case. Most people that use it, I think, end up like me, having to say, there's no default sequence, there's no count, you do what I tell you to do. I'm going to do it constrained random, but I'll tell you when I want to start running sequences and phase-based sequences and all this kind of stuff. So the old code in the OVM, the snippets obviously here, looked like this. John already went through this. I'll not go through it in too much detail. But in fact, this is all convertible with a script that's actually got about that many lines in it. Yeah, it's quite straightforward to convert. In this case, we're replacing sequence utils with object utils. In here, we used to have a p-sequence. The sequence used to be registered with a sequencer. It just so happens we do use p-sequencer thing in most of our derived sequences, let's say. So sometimes we want that, and we can do it automatically. Likewise, the sequencer utils, well, it just goes to component utils. This line here, we just delete, get rid of it. The environment used to do the configuration of the count, the default sequence, well, get rid of it, delete. If this was calling sequence.start, it's the same. This code here hasn't changed at all. Sorry. We haven't done a translation yet. Bear in mind, we're still in OVM here. What we're doing is we're changing the old OVM to have a new style that's going to be directly translatable into UVM. This automatic script, actually, we ran, first of all, in UVM to prove to ourselves everything was going to be okay on the initial set of UVCs that we'd converted. And then it was trivial to convert the script to actually run on the OVM and do the same changes, but earlier on in the flow. There is a little bit of manual repair. I think John also maybe highlighted this a little bit. The one thing we lose from the old OVM sequence library is that a couple of our verification components are reactive slaves. So they're running sequences to generate a response item. And previously they were running a default sequence. It's just the way they were set up. And the default sequence was, generate response items without an error in them, kind of thing. And we had to do some minor changes there. But in this case, we just changed these slaves to start a default sequence in the run phase is how we solved it, but that's details. These are the changes, right? So we did all this, and then we said, okay, let's translate it again. This is exactly the same, except actually we'd already done that. So the scripts are now capable of running a regression in OVM or running it in UVM. It was a manual translation. We did it once. We don't have to forget about it. All the converting to UVM, as I say, we've prepared the database, especially related to the interfaces and the sequences and things like that. And there's some improved UVM features that we haven't yet automated, I would say. As I said, this is only done once. We prepared our OVM database here. This is also a once, this X. But there's a little X down here that sort of could be automated if we followed the same kind of approach as we did with interfaces and with sequences. The reason we haven't done that is simply that we hardly use command args. There's not that many of them. Actually, our base test uses them, but hardly any of our verification components use them. And bear in mind, I'm talking about translating a whole environment here, so it's not just verification components, but also our tests were automatically converted, and our base tests, Testbench environment, which has about 3 lines related to OVM, that was automatically converted as well. I think you can imagine from that once we prepared, we can release. We don't do this all the time. We've got active project with an OVC with check-ins every week, say, and maybe once a month we release a new minor version of that, 1.3. And when we do that, we just kick off the script in the background and verify it, of course, run regression tests in UVM as well as in OVM. So the actual flow for translation, that was the full flow, is just the steps here, And now we can execute an audit script that looks for everything, right? It expects you to have this audit script. It'll throw up a hazard if you say somewhere sequence utils, for instance. It'll just say, you should have translated that already. And likewise, there was 4 little scripts here. They're just called in series. They're bundled together. You can just imagine what's happening here. As I say, key thing here is we did meddle with our OVCs. Now, we could do that because we had live projects running full regressions. So we could, I as one of the project members, could alter that project, could change the OVM and run the full regression and see if I'd broken anything or not. And if I hadn't, I could release it. People didn't even know or care effectively. In some cases, yeah, of course, I had to tell them what I'd done in terms of the sequences, and we had little sessions to explain how the new interfaces work, but that was fine. But that's it. We don't have to touch it again. A new OVCs that are getting generated follow the rules, so they don't even do this translation. They go right in and use the new guidelines, which already have the ideas to prepare it for UVM built into it. Because this is quite slim, I think you can imagine the backward path is more of a possibility now, let's just say. We're all thinking, yeah, but it can't be fully automatic. But you can imagine it's more feasible here when there's no changes, manual changes getting done in the UVM. And that was our goal. Because it's slim, it's possible to reverse it. And we've demonstrated this to ourselves, although in fairness, the forward translation path is quite thoroughly demonstrated. I have to say this is only done in one OVC just to see if we could do it. This kind of approach, if this UVM transition period, I wouldn't think about this at all if the OVM wasn't going to endure for another year. The client's telling us the OVM's going to endure for another year, and we want new UVM projects in parallel. Otherwise, I wouldn't even think about this, I guess. And it's the ongoing projects. We already know we need maybe 2 or 3 UVCs in OVM over the next year. There's a couple of limitations. These things in particular are hard to backport. There's some other things that are a little less trivial, but they're definitely easier. If I was better at scripting, it would be trivial. And even with my scripting skills, it's feasible, right? But these are a bit harder because these are functional. These are just style effectively. This is very much functional. Talking about runtime phases, I think John or somebody earlier mentioned there is still no, even though UVM has multiple runtime phases, it would be false to imagine that there is agreement in the industry. There isn't. And part of that is a fundamental thing. I don't know how it's going to get solved, but I know my preference, and that's, phases are nothing to do with anything other than stimulus. And if you use sequence-based phasing, then you don't care, actually, as it happens. Your sequences, if you've set up if you care about runtime phases at all, then a lot of the functionality can be done in your sequence stuff, let's say. I would say for most users. And if you set it up like that, then it's translatable because it's just sequences. It doesn't care if it's OVM or UVM. And that is simply our guideline at the moment. And not all projects, of course, need runtime phases. And even if you need runtime phases, the big problem or the biggest problem with them is the RTL is not really phased. So you need to be careful. You certainly have to test going out of phase. You have to test out of phase operation between the different things. And that's really quite straightforward to do with sequences, but it's maybe not so easy if all your components are listening to some runtime phasing, some slightly false runtime phasing infrastructure that's been placed on. Now the TLM2, you can either avoid it, you should avoid it unless you need it, and if you need it, you need it. So you can't avoid it, right? The main benefits for the TLM2 are to do with the temporal nature of talking to system C. It's giving much more functionality to test benches that want an agent or a transactor that's talking to system C. And if you do that, well, localize it. Someone might have to totally rewrite that agent, but that might still be a feasible operation for them to backport to OVM. It might not be unreasonable for them to backport. You don't have to worry about it. You don't really have to make that decision. But if you use TLM2 all over the place, for no particular reason, then you've just said, okay, nobody's allowed to backport this UVC effectively. The objection handling is a little bit modified in UVM, but if you don't use multiple runtime phases, the translation backwards is not that significant. And these are normally okay. But bear in mind here, we're talking about writing a UVC with the possibility of backporting it to OVM. The goal is not to cripple your UVM. We do not want a minus VHDL87 switch in here. You're meant to be writing a UVM compatible UVC. And all we're saying is, with a few minor restrictions, if you can see a target in this period for backporting, then think about it, yeah? Think about the isolation, think about how you might write the UVC so that it could be backported. And as I said, we already have examples of this. The register layer is a pretty good example, right? The goal, client goal here is to move, industry goal actually, here is to move to UVM, yeah? But I imagine you guys, everyone pretty much has some kind of transition period if they've already started with UVM. Some of them might have so few OVCs that they just translate them ad hoc and get on with it. Probably not a problem. But if you've got this big overlapping transition period like our current client, then we need to put something like this in place. And as I said earlier, if your scenario is maybe like the guy that was presenting earlier, where maybe you've got, 300 OVCs, some of which came from VMM or URM or some other M, then maybe this isn't such a good fit. My proposal here to actually change your projects. That would also be true, I guess, if your OVCs were in dead projects that had already taped out and didn't have a live regression environment to test them on. That might also be okay, but presumably the old project could be revived purely for the purpose of using its regression environment as a test vehicle. I don't know. You can think about it. You can decide yourself. The key thing from here, as I say, is we prepared the OVM. We changed it. We made a really slim UVM, and we can run it again, tuck, tuck, tuck. Every time we do a minor release in our library of the OVC, we run this process. And although this was developed, we did try the scripts out in some totally different projects. But these projects were also clean OVM environments. And the scripts worked nearly perfectly. They worked perfectly in the original family, and they needed a little bit of hand-holding when we ran them in other examples.
Just a little bit of background. I manage a high-speed serial link team, so SerDes. I've been doing that for about 8 months, so don't let the manager part throw you off. I'm purely technical. I've been doing HSS for 5 years, mixed signal verification. We started an OVM environment probably 4 years ago, starting from scratch. It was a proof of concept. We were moving from Vera to something. We didn't know what it was yet. It was system Verilog based. We weren't sure if it was OVM or what at the point. There were some teams inside of IBM sort of developing their own methodology on top of that. So I'll talk about that a little bit later, but that's really where this is coming from. And in fact, I did the conversion from OVM to UVM myself. I was basically sitting in my folks' house, I think it was the Friday after Thanksgiving, and I said, let me try this out. I'd heard that it was easy to do. From the Cadence side of things, we were involved with Cadence a lot, we still are. And I wanted to see where we really were at. There were a lot of people inside of IBM fearful. They said, it's going to break everything. We're not going to be able to do it. And I just wanted to give it a go and see where we're at. I knew during that period that there weren't going to be a lot of activity in the repository and things like that. So I just wanted to see where we were really at with the conversion. So this is sort of the experience of the conversion that I had sitting in that bedroom, basically starting from that morning into the evening. So the motivation was to position. I look at this as a positional transition, to let the team know that we're getting into UVM. What does it have to offer? I wanted the team to really start thinking about UVM and getting the basis there for them to start applying some of the UVM methodology. It was also to address that fear, that I was getting from a lot of the internal leads. We can't do that. We can't move to UVM. It's going to be too difficult. We got too many projects in flight, and we're going to be broken. Who knows if the tools actually work? So, that's sort of the approach as well, sort of lead by example, and just to see where we're really at. I had nothing to lose. If by the end of the weekend I didn't have it completed, I was just going to go back and address it later. The challenge, a large code base for multiple projects, I'm not sure if it's really large. It's about 100K lines for a single project. If you lump in together, sort of the approach was to do this across all the projects in flight. The legacy stuff would stay OVM. But, if you lump all the projects together, it was maybe a couple 100,000 lines of code. And the general approach was converting using some of the scripts that are available, the OVM-to-UVM conversion scripts, as well as I had to build some scripts on top of that as well to sort of parse through all the directory structure. Again, the OVM development started into 2008, 2009 as a proof of concept. We have 30 days to build an environment, and as the SerDes goes, basically get basic data flow running, data in, data out with checkers. We were enticed because the open source ran on multiple simulators, allowing for vendor evaluation more efficiently. The methodology met all the requirements for reuse as we were going back and forth between some of the internal teams structure they were building on top of System Verilog and OVM. We really realized we were talking about the same thing at the end of the day, and it was just more efficient and more practical to go to an industry standard. We followed the user guide. Anytime anybody asks me for documentation, I point them to the UVM user guide today, but at that time it was the OVM user guide. Where's our documentation? There it is. Use it. That's what we go by. So this was a clean break as well. This was moving from Vera to OVM. The people developing the OVM were in complete agreement that we didn't like our previous environment at all, so we never looked back. We didn't copy anything from that environment. I didn't develop anything that existed from the Vera environment and copy it over. It was completely done from scratch with Cadence's direction and help. We decided eventually to use the RGM package. Initially, we had a special package created by Cadence. The RGM package did not exist. Eventually, we migrated to the RGM package about 3 years ago. So that's worked out well for us as well. And then finally, OVM methodology spread to groups worldwide. Not only am I responsible for a U.S. team, I'm also responsible for 2 teams in India, and there's teams in Burlington. I'm from RTP and New York that are using this OVM methodology. So the proof of concept worked, leading by example worked, and that's what all of our groups under our organization, we have DDR, PCIe, HSS, they're all using OVM methodology at this time. This is just a block diagram sort of what our environment looks like. This actually came straight from some education pages that I go through with new team members. It's fundamental OVM environment. You have your configurations, sequence lib driving the OVCs and the register OVCs. You get a DUT out here, and then monitors sort of collecting in the state. State's a mirror of the config, and that's sort of where our checking takes place in these monitors and really comparing it to make sure the state is what we think it should be coming out of the registers and the I/O. All that stuff's collected through the registers and the I/O. It's just a block diagram to show what we started with. It basically looks the same today. There's not a whole lot of difference between what we have today and what exists in this picture. So this is sort of the process. Prepare the register package first. That was sort of guidelines from the OVM-to-UVM PDF that I received. It said, hey, you need to move forward with OVM RGM 2.5. So that's sort of the first step. Install that. Make sure you can still run regressions. Everything looks the same as it did prior to the updated RGM package. I think prior to that we're using RGM 2.1 or something like that. But this is sort of the baseline for the OVM to UVM conversion. The nice thing about the new parser, it allows for all 3 packages to be generated, and the OVM and UVM RGM packages are identical, so that made things much, much easier for the conversion. We are starting to evaluate the use of the UVM reg, just trying to find time to get into that. So again, we generated the models, everything ran as expected, no hiccups. And in fact, I sort of did the conversion within 4 hours for the entire environment. It was done, much to my surprise, and then there were some other things to work on after that, but I'll get to that in a minute. So I had made a decision in the moment of doing this transition that I would save all of our legacy projects, meaning stuff that's taped out, stuff that we know we weren't doing any development on any longer, would stay and stay as is and stay in OVM. And the stuff that was in flight would all change. And so I moved all of our OVCs to the side and made a copy of them, and those were going to be our new UVCs and UVM. Ran the script on those. I had to build a script around it to sort of walk through all the directories and make the conversions. But so right now we have UVCs basically sitting parallel to OVCs, but those are the things that are updated. Those are the things that change. The OVCs, again, are legacy. Only when we have to go back and maybe rerun, something happens in the lab and whatnot, we'll go back and see, if we can recreate the fail in OVM, but legacy stuff is untouched. It's everything that's in flight and everything going forward in the HSS land. And then I ran the convergence script and it worked. The other thing that I ran into, once I had it converted, I got a fail. Add seekcons IF was sitting there. One big thing that you have to do is make sure you've converted from OVM 1.0 to OVM 2.0. We had done that probably a year prior to this effort. There was this particular feature in the code, but it was completely unused. So all I had to do was go in and comment it out. And magically, the simulation ran. And, the OVM-to-UVM PDF helps out a lot with the descriptions of things that have changed, particularly between OVM 2.0 and UVM 1. The other thing I had to do, and it took me 4 hours to make the conversion and 4 hours to figure out how to compile this thing with the correct options for the GCC compiler, but I had to compile this DPI. When I was trying to run simulation, I was getting a fail. It said it couldn't find some libDPI. I was going back and forth with Cadence that day, that afternoon. We finally had the right incantation for compiling this. I have to compile it for Linux and AIX because it's IBM. We use AIX as well in our compute farm. Got that done, and the simulation ran and passed. And in fact, ran a regression that night, and everything was working as expected. The results were identical to the OVM results. So it looked good, and it literally took me one day. And as I was doing this, I went through and sort of made this chart. In fact, Adam Shear from Cadence went through and made this chart a bit more palatable, but it was basically instructions for how to go through this in a few slides, and it's been blown out. But these are literally taken from the week after making the conversion. So today, this is something that Cadence plus UVM use OVM run semantic. That does is if you don't use the raise objection and drop objection, it allows you to get past time zero in the run phase. We're still using the global finisher or the test sequences. But we still need to get there. So this is still being included. Right now it's about finding time. We are using some of the UVM sort of post-run phase extraction phases to pull some data from the simulation, to see basically for counting checks or things like that. Those will be printed out at the end. And there's ongoing cleanup. Right now we're getting a bunch of warning messages from deprecated code. Basically, most of it is calling the build phase or the super.build phase directly. I've tried to clean that up. I've gone in a couple times. I realized it requires some re-architecture. I've done some of that work, but every time I start it, there's just not enough time in the day to get through it. So still need to get into that, still need to clean that up, and that's going to affect, multiple teams at the same time. So there's a coordination effort that needs to go on across both the US and India to get that done. And then again, adopt some of these new features. The UVM reg we're looking at, the phases we're trying to use. Again, most of it right now is the post-run phases, just to sort of extract data from the simulation and make it part of the log file. The results were good. I basically, again, documented everything I did, passed it to the India team, said, hey, let's get on board with this. Let's everybody be in the same area, working with the same UVCs. And they did it. Over the last year and a half, all of the projects that, are basically in flight at the same time, which is anywhere from 4 to 6, have been converted. Right now there's 4. And everybody's using it effectively, no problems. We are still looking at cleaning up and starting to really adopt the methodology and massage everything. Again, this is all about positioning for me and the team. It's getting the team to start to think about UVM. The effort was low. Like I said, I did it on a Friday. I was done by the end of the day, and I've since passed all this information on to the team members to make the same conversion. But the effort was relatively low. Again, I spent more time trying to compile that DPI file than I did making the conversion. About 100K lines of code, that's a single project. Again, it's a couple 100,000 if you include all the projects. And the motivation is real. Again, it's that OVM is twilighting. It's positioning the team to be able to take advantage of the new features that are available. And that's really why I went through this effort, is to position the team to be able to better utilize the UVM methodology.
I'm the principal verification engineer at Altra. And our current project is we decided to move into UVM. We split the outline into a couple of things, overview and some of the challenges we faced moving into UVM. And the overview is basically why we want to talk about our previous Verilog-based verification environment we had and why we moved into UVM, and also little bit on the new UVM-based verification environment and how it applies to FPGA verification flow. The challenges here is basically, as most of the FPGA is big programmable logic core, and therefore doing verification it's a lot more complex than doing ASICs or ASSPs. And also the other things we wanted to do was we wanted to take our legacy code and then basically see how we can integrate into our UV environment, because given the time frame, we cannot do everything and then meet the tape-out schedule. And on top of being programmable core, also all our I/O is highly configurable, and that needs to be also taken into account. And also we have a lot of interfaces, and we were using a lot of external VIPs and internal VIPs, which we need to integrate inside the UVM environment. A little bit on our Verilog-based environment, what we had before. Basically, we were using Verilog-based and system Verilog-based environment, and we had multiple test benches with multiple interfaces, and each needs to be recompiled. There are a lot of recompilation of tests and stuff. And also there was no object-oriented programming concepts, therefore less reuse and then more, and also not scalable. And basically reuse was copy and change things around, which was working fine, but long term it's not possible to do this thing. And maintaining different types of test benches and different types of environment, it's over a period of time, this itself becomes a big task. But the biggest advantage we saw was as most of the other companies themselves also gone through this, basically we had a lot of designers who can do debug and help us, and that sometimes they'll also be willing to do some pitch in for some verification work. And that's the biggest advantage of using the traditional Verilog-based environment. The reason why we moved into UVM, and based on the previous slides, we cannot keep continuing with our verification methodology. We need to change the verification methodology. We cannot continue going forward with chips becoming more and more complex and a lot of interfaces being done. And some of the reasons we decided, okay, we will go to UVM is supported by Accellera, and all the EDA vendors are supporting UVM, and it brings in the object-oriented programming concepts. Therefore, we have reusability and scalability. The reusability is for example, we can do vertical and horizontal reuse where we can share components between our IP teams and subsystems, and horizontal for future projects. We'll be able to reuse a lot of these interfaces. And it comes with a base class library, which we can use it as template and develop things on top of it. And also, other people are talking about, a lot of VIPs are now coming with UVM-based VIPs. Therefore, we can easily plug in all the interfaces with our new, with the UVM-based VIPs and into our environment. And the major advantage of, from my side, I saw was it had good online documentation and a lot of UVM forums, a lot of problems I had. I can go to UVM forums, and most of it I can easily find solutions for if someone has already gone through it. And there is also a lot of online training available, and there are a lot of vendors who do on-site training for people to bootstrap UVM very fast. And then online training, one of the good things, you can do it at your own pace when you're comfortable. And I think I have used a Verification Academy a lot, and it was very helpful. And the major disadvantage from the previous slide, again, this one is all the designers are not used to object-oriented concepts. Therefore, it's the debug becomes more challenging, because before they were helping you debug a lot of stuff. Now you have to come up with some kind of interface for them to understand and help debug. But long term, this is okay, because once you get the UVM and then you have the flow, and then people start understanding, you do training and stuff, this becomes manageable. This kind of gives a high-level picture of our verification environment, but still some things are missing in this. But this kind of shows on top of using developing everything on our own, we were reusing a lot of components which is already available, and reusing a lot of stuff from the previous environment, so that everything is not from scratch, and then so that we can meet time for tape-out as well. This white box is our kind of gives a FPGA, how the FPGA is. This one is FPGA fabric core, where you can program user logic and do all sorts of logic in this. And then all these blocks around these things are all hardened IPs. Basically, a lot of high speed and serial interfaces, and you have memory controllers, a lot of memory controllers supporting all the memory protocols, and our core interfaces for the programming the core logic. And if you see the color coded, all these blue coded are the ones UVM agents or UVCs which we have developed, and these are a couple of scoreboards. And also this is Avalon proprietary Avalon bus we are reusing from another group with the UVM wrapper on top of it. And all these orange boxes are all the Verilab modules, which we got it from our previous environment we are using. And then there's a configuration resource database for configuring the whole environment. I think now Charles will talk about a little bit of our UVM-based verification environment and how it applies to the FPGA verification flow. Later on, I think we have a few more slides to talk about VIP's integration.
Oh, thank you, Ravi. So the new UVM-based verification environment, we re-architect the environment from scratch. Basically, we look at the DUT and identify the interface that connect to the DUT and develop our UVCs that actually associate with those interface. Then we build the verification environment surrounding those UVCs. So now we have one unified verification environment that's supporting the multiple operating mode, compared to the previous environments that we have multiple environment running with supporting the multiple operating mode with multiple simulation executables. And also we significantly reduced the number of tests by using UVM inheritance and the configuration settings. So that eliminates the need to writing lots of tests to do using a copy and paste. Now the current UVM-based tests are only about 1/3 of the tests we had before. So also the simulation performance also improved by compiling. Because we only have one executables simulators, and we just need to compile once and run all the tests. And we also improved compilation and run and regression flow, rewrite the tools to support all those tasks. And with UVM command line processor, which is built-in and free, which has helped us a lot. Don't need to worry about passing the test name or verbosity, all of that. We just pass this to the UVM. So now I want to talk about the FPGA verification flow. So it is a little different from what we usually think about ASIC verification flow. So FPGA verification flow, we have an extra step that is that programming the FPGA. Basically, we're loading a user logic image into the FPGA. So that image will contain the settings for the core and the setting for the I/O systems that can use as a user mode logic. So for the configuration loading, it supports multiple programming interface. It includes the parallel. It could be a parallel and serial data pin that connecting to the FPGA, or it can be a flash device that contains the image and that is connected through SPI bus to the FPGA. Or it also can be through PCIe interface remotely setting into the FPGA. So, and also the data is compressed and also can be encrypted due to the, to just save some space and for some security reasons. Also, we support front door and back door loading of the configuration to the core and the I/O system. So the reason is that the front door, since the size of the image could be fairly large and it could take a long time to load. So when we're running a user mode task, we don't really to go through the front door again. So we provide a backdoor load mechanism so that we can go to the user mode very fast. So the verification goal here is to make sure that the programmed image matches with the expected image we have with using a control block models. So after the FPGA is loaded with the configuration, then we'll be in user mode. It's just as the basic test bench need to support that we can generate the stimulus to the DUT and also checks output to see if it's correct, just as normal ASIC verification. But however, in our case, the goal is to verify the underneath FPGA fabric and the I/O system to see if those are functioning correctly or are they connected properly. So as a ASIC verification, we are actually checking the user logic to make sure it works. But in our case, the user logic is just a mean to verify the underneath blocks. One of the challenge we have is that due to this highly configurable of the FPGA, right? So the user can program the FPGA to any logics. So how do we make the verification environment configurable so that we can use the one verification environment to test all those kind of user logics? So I'll talk about on the next slides. So to answer to that is that we create a core logic UVC, which is a highly programmable user verification component. It's connecting to hundreds of the GPIO pins. And if you look at the block diagram here, it's include agent, monitor, driver, sequencer, and config, just as normal verification component. But it's highly configurable. The user can decide on which pin to drive, what data to drive, and when he's going to drive it. So these are all configurable through the UVM configuration and the sequences. So in this case, we have, in this UVC, it supports multiple agents. So the agent can be 1 to n agent, and each agent can associate with 1 pin or n pins, and which pin to drive using that agent is also configurable. So all of that are configurable. And also, we have the driver. There's one feature is that we can drive the signal synchronous to a specific clock, or we can drive the signals with a specific delay. So if you think about that, so this component actually can use to drive any kind of synchronous signals or asynchronous signals. And all of this is done by, without recompiling anything. We can use this to just verify all the different kind of user logic with one executables. So this one is also used by our software group that was a Cortex software, which is the synthesizer to the user logic to verify the customer designs. So in our case, we have lots of the Verilog-based verification component available for us. Due to the time constraint and usually for the project, so usually we have to live with a verification environment that have both UVM environment as well as some of the legacy VFM or the Verilog-based models. So we use the interface as a clear division and also a communication media between the two worlds. Also, the interface are bind to the signals. Some of the VFMs are pretty independent. Sometimes they, you just need to configure them and then connect them, and they can run by itself, and you don't need too much user interaction. But some of the VFMs that actually need lots of user interactions, so we create a UVM wrapper around that VFM so that from user point of view, it will act more like a UVC. So we also use the interface to implement assertion. Then the interface are actually binding to the modules or binding to some specific physical signals. So as I mentioned before, the FPGA core is highly programmable. Also, the I/O system is also very programmable. So there's a lot of different interface we need to integrate into our system. There's a lot of hardened IP in the FPGA. Also, there's some softened IP which user can implement into the core that actually connecting to the I/O systems. So then we need lots of the verification IPs to verify all those interfaces. So in the user mode, basically the configuration space is huge. So in order to make a reasonable effort to integrate all of this together, so UVM actually help us a lot in this sense to glue all those together and create a homogeneous environment for the test writer to work on. Also, we have internal resource allocation tools that actually help allocate the resource in the FPGA so that the test writer can have a specific file format or have some spec. Then the tool actually going to create the image and also the configuration for the environment, basically. And here I mentioned a little bit about the configuration space is huge, so that we have thousands of those configuration, and we actually try to use a UVM reg model to handle that, and we found it's not a clear solution for us. So we basically used our homegrown tools to do that. Then let's go back to Ravi.
Okay, thanks, Charles. The VIP integration, another big thing for us, because we need to deal with all these different interfaces, 1G, 10G, 100G, PCIe, all types of PCIe protocols. And then we have our own proprietary bus, Altera Avalon proprietary bus. And then also we need to develop with all sorts of memory protocols, DDR2, DDR3, and everything, whatever it's there. And therefore, we need to have some kind of environment where we can add these different VIPs from different vendors very easily, and then it should be configurable from UVM test. Therefore, we have written some proprietary tools again here to basically, and then wrote some constraints on top of it. How do you want to connect these VIPs? How the connections are done? And once we have that, then what we have is like, basically we have an environment where we can bring in different VIPs and integrate different VIPs from different vendors. And the main problem with the integration with the VIPs is like, one thing I found is like with dealing with the different vendors. On the top level, from the UVM side, it's kind of similar, but at the lower level, the integration is like completely different from different vendors. If there's some kind of common standard, that will really help. But nevertheless, it's better than using a standard non-UVM based VIP where you need to go through all the specs and understand all these different calls and then do that in your environment and plug it in your environment. UVM VIP really helps in that level from the user perspective, from the test writer perspective. And once we have all these different UVM VIPs, like now we are at a point where we can easily do a lot of proliferation products, like for a different same, usually FPGA comes with there, a lot of proliferations comes with the same FPGA, and then there are very, very short turnaround time for tape out. And basically we can easily swap in these different FPGAs with different interfaces and then get going. And also down the road, like we have all this new FPGA family coming with new different interfaces on top of what we already have, it then everything makes it easy for us to go forward. Okay. I want to show a little bit on our integration of our existing, we do a lot of reuse for our UVM environment, not doing everything in the time frame. Like I said, eventually the goal is to move all these things to native code, but for the time being, for tape out, we need to get these protocols integrated in our UVM environment. For example, Altera, they have Avalon BFM, which they give it to external customers. And we found out, we are trying to figure out, it's impossible to write this thing from scratch in the time frame we have. And we found out, one of our system solutions group, which works with external customers, they had to deal with this. Therefore, they had written a UVM wrapper on top of it. And we basically, since it's a UVM, we were able to just easily, with some modification, we were able to pull in this thing into our environment. Like if you see, there's a master and slave. These are all Verilab modules, and then these are all instances of Verilab modules, and then this is the system Verilab interface, and then you have this agent, and basically they use the HTTL path to bind these things together. At the top level, the test writer needs to say which instance he wants to write, and then and then you can bind to those instance modules, and then they are connected to the pins. Summary is this is the first full chip verification project in UVM in Altera, and then we had some of the issues how to, within the UVM environment, how to do the programmable stuff, and then also deal with a lot of reuse with both internal and external. And the reuse helped us a lot. Otherwise, we couldn't have done this project within the time frame, doing everything from scratch. And UVM basically provided us a clear way of configuring a lot of things from the top level. A lot of things I haven't shown is we have a lot of C-based calls, DPIs, and also other stuff we are using from the old environment. And also we have a controller block model which is written in C, which has been used for a long time. Therefore, we were able to link that with the VCS, and then from the UVM we were able to call from those how to generate those images and stuff as part of test writer. Therefore, this UVM provided a big way of configuring everything in one place. And then also a lot of reusable, going forward, we can basically take all these components, and then all the groups can reuse it. We are already working on some kind of a verification repository inside Altera where all the groups can start reusing it. And also going forward, this is not completely done, but what we want is we have a basic environment. Once we have it for the next project, we will do a lot more in the UVM, doing a lot of native stuff, and then a lot of randomization and stuff. But this is the first step for us to get going, and then we are almost 80 to 90% done. Another 10% work is done.